Alrighty, let's see what we got. We have, you can use antiderivatives to solve definite integrals using whatever FTC stands for. So what conclusions can you draw from this image? So you should take a look at this image, and you should think about what you're seeing and what connections you see. One easy connection is right down here. You have y equals 2x plus 3, and you have x squared plus 3x. You should pretty quickly see the derivative of x squared plus 3x is 2x plus 3. So that means the green line is the derivative of the blue curve. As I look at numbers, you should see if I take 154 and I subtract 40, I get 114. So that means if I take, let's call this F and this G. If I take G of 11 minus G of 5, I get this trapezoid. But if I think about what we've been talking about, the area of this trapezoid is the integral from 5 to 11 of f. It's the area under the curve. So the area under the curve for f from 5 to 11 is the difference between g of 11 and g of 5. But g is, the derivative of g is f, so g is the underderivative of f. So that means if I can figure out whose derivative f is, so in this case the derivative of g is f, and then I can plug in these numbers, I can figure out what the area under the curve. In this case it's a trapezoid. I could have done that in geometry. But I could also do it for other shapes. So let's formalize this. The fundamental theorem of calculus, there are two parts to the fundamental theorem of calculus. You can teach them in either order and talk about them in either order. We're going to talk about this one first. If little f is blank on AB and big F is any blank of F, well, big F has to be an antiderivative, right? Antiderivative of F. Then, so if F is blank on AB, so that reminds me of like IVT, EVT, MVT type statements. So if I'm thinking about finding the area under the curve, I'm going to go with continuous. If F is continuous on AB and big F is any antiderivative of F, then, well, we said if we integrate from A to B of little f, we get the difference in big F. That's what we just talked about on the previous page. Now I skipped the middle step because the middle step is a notation piece. So what I want you to do is write down what the antiderivative is, write down what the underderivative is, write down whose derivative at little f is, and then you put this evaluation bar from A to B. That evaluation bar is not anything new. We saw it with derivatives. We found the derivative of some function when x equals 2. That's just that evaluation bar. We're just using it in a different way here, but it's the same general idea. So we have a function, we find its antiderivative, we plug in numbers. I think we can handle this. So there's a bunch here. I will do a few. So let me pick, say, this one. So we have 3x squared. Well, whose derivative is 3x squared? That would be x cubed. We have 2x. Whose derivative is 2x? That'd be x squared. And then we have 1. Whose derivative is 1? That would be x. So we evaluate that from negative 1, not negative 3, negative 1 to 3. And we plug in. So we've got 3 cubed minus 3 squared minus 3 minus negative 1 cubed minus negative 1 squared minus negative 1. So when we do that, that's 27 minus 9 minus 3, which is 15, minus negative 1 minus 1 plus 1, so negative 1, so minus negative 1, which is 16. For number 5, I'll give you a hint. Just multiply that out, and then you'll be able to do it. Number 6, let's go ahead and do number 6. My first step is to rewrite it from 1 to 8. X divided by x, the cube root of x is x to the 2/3. And then rewrite this as 2x to the negative 1/3 dx. The reason I did that is because now I can just power rule that. So x to the 2/3, add 1, that's x to the 5/3. But wait, when that 5/3 comes down from power rule, there'll be a 5/3 in front. So I need a 3/5 here because I need a 1. So when the 5/3 comes down, when we take the derivative and 5/3 comes down, 5/3 times 3/5 is 1. Similarly, we have x to the negative 1/3, so that's going to be x to the 2/3. I need a 2 to come out of that. So I need, when the 2/3 comes down, I need to multiply 2/3 by something to get 2. Well, that's going to be 3 if you solve that equation. And I evaluate that from 1 to 8. So that's going to be 3/5, 8 to the 5/3, minus 3, 8 to the 2/3, minus 3/5 minus 3. I'll let you finish the calculation there. Let me talk about number 8. We have 4x, so whose derivative is 4x? That would be 2x squared. And then we have secant squared. Whose derivative is secant squared? That would be the tangent. Then you plug in pi over 4 and 0, and you'll get to an answer. Feel free to play with any of the rest of them on the page, and ask questions if you got them. All right, let's see what we got here. So now we're going to use definite intervals on the area between two curves and calculate average value. So we have a request to calculate each of the requested integrals. So there's some basic integration stuff we're doing here. I'm just going to do this using area. I'm not going to do it using FTC that we just learned. So that's 6 by 2. So the area of that is 6 because it's a triangle. That's 1 by 3. So that's 3/2. So if I were to do the absolute value, that would make this bounce up. So we do 6 plus 3/2, which is 12/2 plus 3/2, 15/2. Versus this one, which would be, that's a negative 6 plus 3/2. So negative 12/2 plus 3/2 is negative 9/2. But then take the absolute value of that. So it depends on where those absolute values are. How would you find the area between the curves? Think both absolute value and without absolute value. The blue curve is F, the red curve is F, blue curve is G. Forgot how to talk there. So let's talk about, let me zoom in a little bit. Let's talk about, it looks like these curves intersect somewhere in here, I don't know where, and they intersect somewhere in here. So suppose we want to find this area right in here. Ooh, I missed an intersection point as I was coloring. So let's talk about not that intersection point, but this one. So if I wanted to find that yellow area, wouldn't I do the red curve, which I'll do in pink, and then subtract the blue curve? Wouldn't that work? So I would integrate the red from, say, a to b, and then subtract the integral of the blue from a to b. So integrate the red from a to b, and then subtract the integral of the blue from a to b. All right, but what if I want this area right in here? Because it looks like the red was higher, but then the red is lower until like here, we'll call it C. So in that case, wouldn't I do the integral from B to C of blue minus the integral from B to C of red? Something like that. So I'd have to do those pieces in two. I'd have to do that in two different pieces because these curves flip-flop over each other. I think that's all I need right there. I think I'll let you ponder on how that works and why that works. I think I'll leave it there. Alrighty, now let's see. Consider this function. If we took the area under the curve, forced the area to be all the same height, what shape would we form? Okay, so we have, so the area under the curve, let's find that. Area is, it's 6 by 3, so that's 18, 9, because it's a triangle. And if we forced that area to all be the same height, so I'm going to say keep the same width, but the same height. So what height would I need? So 6 times what is 9? Well, that's 3/2, so that's like 1.5. So oh, okay, so that's going to form a rectangle. Now consider, what's the relationship between that shape, its area, and calculus? So the area of the rectangle is going to be the same as the area under the curve. And so the area of the rectangle is the same as the area under the curve for the black triangle. And if I were to talk about, okay, so I've got calculus, so I've got the area, let me write this down so I don't confuse things. So the area of the triangle is equal to the area of the rectangle. Those are equal because we kind of built them that way. We forced the height to be 3/2 because we want all the same height but the same area. And we'd form a rectangle. And let's see, the height of this, it's got to have something to do with average of these values. So if I take all these y values, this height here has to do with an average. It's making me think of some of the stuff we've done in previous courses. Oh, okay, let's consider a different curve and do the same process. So let's suppose we have from here to here, we have this green area. So let's estimate it. That's a bit bigger than 4. So that means like somewhere in here we'll have a rectangle. That should probably be higher. I regret that decision. Let's go ahead and make it a little higher, maybe here. That area looks a little better, maybe even a little higher it should be. We'll see. That sounds like Yoda. So the purple area is the same as the green area, but the height of the purple is still going to be something with the average of whatever the black curve is. All right, let's go to physics. Let's think of this in terms of physics. What would the average value be for this function 0 to 0.7? Well, let's see. This is a trapezoid. I'll think of it as 2 triangles because that makes more sense in my brain. So I have a triangle that's 0.7 by 60. And then I have a triangle that is from 2/10 to 4/10, so 0.2 by 60. So when I do that area is 27. So that area is 27 kilometers. Because we did kilometers per hour times hours, so that's just kilometers. But the average value, that would be, from our discussion we've had a little bit, that would be kind of a height in here. That would then be, take that 27 kilometers and divide by 0.7. And so I've had 27 divided by 0.7. That's 38 and a bit. So 38.571-ish. And that's in kilometers per hour. Okay, so the units, that's the velocity. So that's the average velocity over that interval, where I had a pretty high velocity up here of 60 kilometers per hour. But as I got to it and as I went away from it, obviously I went slower than 60. So the average was that 38. So what did I do? I found the area from A to B, and then I divided by, so if that's B, that's A. Didn't I just divide by the difference? Oh, that's like a mean, right? So you add things up. That's what the area does. And then you divide by the width. So to formalize it, the average value of a function is going to be the area, so integral from A to B of some function, divided by the width, which if we think back to when we first started finding average, mean, that makes some sense.